Hello, my name is Ospelkaus and I'm an experimental physicist at Leibniz Universität Hannover and PTB in Braunschweig. My team develops new quantum control techniques for fully integrated quantum processes based on trapped ions. Quantum computers hold great promise to solve challenging problems of humanity completely inaccessible to any supercomputer. Breaking this wall will enable new drugs to be discovered, new materials to be developed, and give us fundamental insights into the collective behavior of quantum matter. Trapped ions are one of the most advanced systems on the route towards large-scale quantum computers. The two states of the qubit are encoded in two suitable energy levels of the atom. We love ions as qubits because they can be manipulated very precisely. We can hold on to the ions by grabbing them with electric fields. In this chip trap, voltages are applied to the chip to suspend the ions in free space above the chip surface. So we can store the qubits in chip-scale devices. However, most present experiments require bulky laser systems much more complicated than even the one in the background here to implement elementary quantum gates. The problem with this is that the laser systems are difficult to maintain and the alignment of the laser beams to the individual atoms requires a lot of tender love and care. Building on work that I started as a postdoctoral researcher at NIST, my group has developed a technique that lets you implement all quantum gate operations using just electronic signals, specifically microwave signals. That is incredibly useful and powerful because for quantum gates we can now leverage mature electronics that is found everywhere, from fighter jets to cell phones. We have developed a carefully designed coil that can be embedded into an ion trap chip. A microwave signal applied to the coil is sufficient for all quantum gate operations. Most recently, we have found out that a specific pulse shape of the microwave signal lets us carry out quantum gates in a way that is extremely robust to experimental imperfections, so that a whole school class can run through the lab and things will still work out okay. This is not only good for outreach activities, but the quality of the 2-qubit gates is now approaching a 99.9% success rate, with one more 9 to go until the threshold for the application of error correction protocols and thus for scaling is reached. What needs to be done for that is now well understood and appears doable. The logical next step for us is to realize a universal integrated quantum core with separate registers for initialization, storage, computation, and readout. In Lower Saxony, we pursue this goal together with my colleagues in the Quantum Valley Lower Saxony Q1 project. In the future, we would like to integrate even more control techniques for ion trap quantum computing at the device level, for example integrated electronics, so that we come closer to our vision of a fully integrated and scalable ion trap quantum computer to address so far inaccessible challenges.